And sorry, guys, I'll just go over that again because I've just started the recording. So, yeah, circuit protected devices, they're essential components in electrical systems designed to prevent damage and hazards caused by the faults we were looking at a couple of weeks ago: overcurrent, short circuit, earth faults, and voltage surges. These devices interrupt or limit electrical flow when faults occur, safeguarding wiring, equipment, and human life. So they're important because they prevent electrical fires caused by excessive current. They protect our appliances and machinery from damage due to surges or short circuits. They ensure safety of personnel by reducing shock hazards, and they maintain the reliability and longevity of electrical systems. Cool. So far in your guys' career, what kind of circuit protected devices have you guys installed, or what do you deal with on a daily basis? ICDs, fuses, RCBOs, yep. MCBs.
Stuart, usually with the food machinery side of it, we just deal with either MCBs on the appliances or sort of phase rotation detection for like mixers and that. Some mixers will have that installed.
Yeah, so they come with like current reversal protection devices as well as MCBs and things like that. All good, Casey. So yeah, does anyone know what I mean when I say an M? So we have MCBs, which are miniature circuit breakers, but has anyone dealt with any MCCBs? So an MCCB is what is called a molded case circuit breaker, and those are the kind of bigger circuit breakers that you kind of see in the high voltage or the main supply side. So instead of being DIN rail mounted, normally they've got their own type of mounting. So the list of stuff we're going to go through tonight, the different types of circuit protected devices. So we've got your MCBs, your miniature circuit breakers, which protect against overcurrent and short circuits. Your RCCB or RCD, residual current circuit breaker. They detect leakage currents to prevent shocks. Your RCBO, which is an RCD with overload protection. HRC, your high rupturing capacity fuses. Cartridge fuses, rewirable fuses, overload relays, and surge protection devices. Okay. Can everyone see the PowerPoint? Is there anyone who can't see it?
All good, Stuart.
Okay, yeah, I figured that might be the problem. Uh, it- okay, can everyone see it now?
Nah, bro, I can't see it.
Yeah, the only two options for me are to share screen and then to also share to the what do you call it? To the like use the PowerPoint in the actual Teams meeting or to share the entire screen. More people seem to be able to share the entire screen, but I will obviously be talking through the points. It just means that those of you who can't see it, I will remind everyone the link for the. I do post them onto a separate YouTube channel for you guys to be able to watch it afterwards. Cool. Cool. So we talked briefly. We did some revision. So the types of faults. So you got your short circuit faults. So that's a dead short between either phase and neutral or phase and earth. You got your overload faults, which is a steady increase in current to the point where it's more than the breaker or fuse is rated for. And you've got your earth leakage faults, which is slow current leakage from neutral to earth or phase to earth. Cool. So short circuit occurs when supply voltage is applied to a circuit with negligible impedance. And we talked about impedance. So impedance is the AC version of resistance because there's more than just pure resistance that we need to worry about, which you guys will learn about in second and third year when we start to calculate that. So prolonged faults cause severe damage through heat, explosions, fire, and electromagnetic forces. These forces can distort or dislodge cables and buzz bars, sometimes throwing cables off trays if not secured. The size of the arc, fire, and explosion during a short circuit depends on the available power. And those of you can see that. So yeah, that's big meaty cables on a cable tray and a short circuit. And as you can see, there's a lot of force that can be applied because that cable ladder is bending like nothing else. Cool. And then yeah, so trees near overhead power lines can cause arcing. It can get so bad that arcs form, trees catch on fire, and then eventually the high voltage line or overhead line will snap. So when we talk about overload or overcurrent, it occurs when a circuit draws excessive current beyond normal levels. Prolonged overloading generates excess heat, damaging insulation and conductors, potentially causing fire. While equipment and cabling can endure brief overloads, damage depends on current intensity and duration. And then when we talk about earth leakage, so earth leakage currents is unintended current flow from a phase or neutral conductor to earth, often through insulation. Outdoor or human environments can cause moisture ingress, creating unintended paths for current flow. More moisture increases leakage risk. The metallic frames of fittings or equipment can become live, creating a hazard. If poor earthing exists, touching the metal while grounded may cause electric shock. So here's that list of circuit protector devices. So MCB or your miniature circuit breaker, RCCB, residual current circuit breaker. It's the correct name for an RCD because an RCD just means residual current device, whereas a board mounted RCCB is a residual current circuit breaker. And your RCBO, which is basically an RCB and MCB in one. HRC, high rupture and capacity fuse. Cartridge fuse, rewirable fuse, overload relays, and surge protection devices. So miniature circuit breakers protect against short circuits and overcurrent. They come in single, double, and triple pole variations, with some allowing modular interconnection for automation. MCBs are a bimetallic strip for thermal protection and a magnetic coil for instantaneous short circuit response. which will be covered in this lesson. So when it talks about allowing modular interconnection for automation, that means if you've got a 25 amp circuit breaker for your motor, three-phase motor, but you've got a 6 amp for your control circuit, you can interlink those so that way if the 25 amp breaker trips, it also kills the 6 amp, as well as if the 6 amp trips, it kills the power to the 25 amp. So that way, if circuits can't be, if one trips, the other one needs to turn off as well, you can interconnect those circuit breakers so that they all turn off at the same time. Cool. So we've got a side-on view for those you can see. So we'll go through the parts inside. So you've got a bimetal strip, a trip lever, a trip spring, your main contacts, the solenoid coil, which also trips the trip mechanism. Trip mechanism, trip lever, and you've got an arc chute. So there'll be a video talking about the arc chute later. But what it does is if there's an arc between the incoming and outgoing sides of the MCB, that arc will travel up to the arc chute. And because those plates are not electrically linked together, the arc will try and jump across all of those and lose its energy and dissipate. Oh yeah, if you do come to the training center here for your block course, and I have talked to the staff, the admin staff about block course, and they should be sending out the reminders and notifications for block course soon. If you haven't already got it, it should be coming out very soon. MCB characteristics, so voltage rating. So the maximum voltage a device can operate continuously without risk. Exceeding this can break down insulation and damage the device. The one here, so its operating voltage is at 230. So that's its operating voltage. So its breaking capacity is the max short circuit current it can handle. This one's rated at 10,000 or 10 kA, which is not normal. So normally you'd get 6 kA, 10 cost more. And then so its tripping curve is class B. It's H rupturing capacity type, and it's a 25 amp breaker. Cool. So it's rated current. So yeah, the maximum current device can carry continuous. So that's its maximum breaking capacity is 10,000. It is not the value at which the device operates. So here there's an MCB operation curve. So up to 50 amps, tripping is controlled by the bimetallic strip. So it's a thermal action. As current increases, trip time slows until magnetic action takes effect. So the way the bimetallic strip works is that because they're two dissimilar metals, one wants to bend, heat and expand more than the other one, and so it bends more in one direction than the other, causing the trip mechanism to actuate. So between 50 and 500 amps, both thermal and magnetic effects contribute. The magnetic effect then causes a steep drop, disconnecting the fault rapidly. Above 500 amps, tripping is solely magnetic, reacting more effectively to high fault currents than the bimetallic strip. So there are different types of MCB, also known as curve. So sometimes they'll be called B-type, other times it'll be B-type, C-type, and D-type. They'll be called B curve, C curve, and D curve. So if you look at a breaker and it says a C10, it's a C curve 10 amp breaker. So a B-type has a fusing factor of 1.25. It trips instantly at 3 to 5 times its rated current. So a 10 amp MCB trips at 30 amps. C-type MCB has a tripping factor of 1.5 and instant trips at 1.5 times its rated current. It's the most common in New Zealand because we use it all through domestic. D-type tripping factor 1.75 to 2.5. Instant trips at 10 times rated current. So it's used for motors and high inductance loads with high inrush current. Cool. So the fusing factor or the tripping factor is the ratio of a protective device's rated current to its minimum fusing/tripping current. A lower factor means operation closer to the rated current. The relationship follows this formula. So your fusing factor equals your fusing current divided by your current rating. So a 16 amp MCB at a minimum current value of 24 amps, as tripping factor can be calculated as tripping factor equals 24 divided by 16, which gives it a tripping factor of 1.5. So the MCB operated at a minimum of 1.5 times its rated current. So the tripping factor of a type D is 1.75 to 2.5. At instant trips at 10 times its rated current. So the reason it's used for motors and high inductance loads is because when a motor first turns on, it has a high inrush current due to the inductive nature of a motor. There are other ways to start a motor to decrease that inrush current, but you also need to use the correct type of MCB or HRC fuse along with it. don't know why my mic was off there. So MCB, it's got two mechanisms, the bimetallic strip and the solenoid coil. As the video said, the bimetallic strip takes a while to heat up and activate. So if there was a spike of, say, 60 amps flowing through a 6 amp breaker, it would take ages for the bimetallic strip to heat up and bend. In the meantime, there could be fire or shock hazards apparent. So we need to make sure they trip properly. Cool. So RCDs or RCCBs. Cool. So the term RCD stands for residual current device, whereas RCCB stands for residual current circuit breaker, and encompasses all devices that operate on the principle of earth leakage, which we'll discuss shortly. There are a number of devices that work slightly different, but we just got so other names for RCDs are ground fault interrupter or GFI, which is what Americans call it, earth leakage circuit breaker, ELCB or safety switch. In New Zealand, we widely recognize simply RCD. Cool. So the principle of operation, so the residual circuit device or RCCB operates on earth leakage current. So this is when flows from a live conductor to earth, phase or neutral. It generally indicates a breakdown of insulation or moisture in a fitting or device. Either way, it's a type of fault that can be very serious, as it means there's current flowing in the earthing system and potentially metal parts and fittings can be live. The RCCBs protect against this type of fault by indirectly measuring the current flowing in the earth conductor. This means measuring the current flowing in the phase conductor and comparing it to the amount flowing in the neutral. So a circuit that is operating correctly will have the same amount of current flowing in the neutral conductor as the phase conductor. However, if there is a leak to earth, then there will be more current flowing in the phase conductor than the neutral. So Ohm's law tells us this. Cool. So this is an example drawing of the inside of an RCD. So you've got the sensing coil, which is also known as a toroidal coil, and it's got a phase and neutral flowing through it. And because it's got the phase and neutral flowing through it, the induction that's caused by the current flowing through the cables is negated by each other because they're in opposite directions, meaning there's no current flow in the coil. But as soon as there's current flowing in the coil, it will generate enough current to activate the trip actuator, which will disconnect both sides of the line in neutral from the circuit. Cool. So it uses electromagnetic induction to monitor the current flowing in the phase and neutral conductor. That pass through the center of an iron core that has a secondary circuit around it. A single conductor would usually introduce a current into it, but because the two are opposing each other, they cancel each other out. So when there's an imbalance between phase and neutral, current flows, magnetic field is induced in the toroidal coil, activating the sensing coil and activating the trip actuator. And if you notice, there is a test coil there. So the test button is pushed with a resistor, which is connected to the neutral, and then connected to the phase and then back to the neutral, but on opposite sides of the coil. This means that it induces a slight inductive field into the sensing coil, which then activates the trip actuator. So that's all the test button does, is check that the RCD is working. It doesn't test that it's actually tripping at the correct current. It's just a push button test. Cool. We can detail the stages in which it operates. The diagram here has a high resistance fault between phase and earth, allowing a small amount of current to flow. So following the sequence of the events, the RCD operates. So the circuit is energized, allowing current to flow through the load and fault in parallel. The result is more current flowing in the phase conductor than back through the neutral. The difference causes an imbalance in electromagnetic fields, causing electromagnetic induction to occur in the sense coil. The electromagnetic induction causes an EMF to be generated in the secondary sensing circuit. Current then flows through the electronic equipment. As current flows in the sensing circuit, it gets amplified and causes the trip relay to operate. The contacts of the trip relay latch open and interrupt supply to the circuit. The circuit stays open until the RCD is manually reset. and pretty much all of your RCDs or RCCBs will be manual reset. And even your MCBs, if you hold the MCB, like you see so many people take photos of MCBs not being able to activate because they've wound some copper wire and attached to a screw. Internally, your circuit breaker will still activate. Even if the switch is held shut, the circuit breaker will still activate. It's just that the switch won't move. As soon as you let go of that switch, it'll flick down. So yeah, we talked about the test button with the resistor in the circuit diagram. This is a requirement for all RCDs, so the operation can be verified at regular intervals. There's a circuit between the load side and the sensing ring and the neutral on the supply side. And so when the test button is pushed, the current proportional to the resistor value flows in the circuit. It's effectively simulating a fault. This ensures that the RCD is operating. So it is just a functionality test. It does not count as doing an operational test. You still need to do your operational test to ensure trip time and the trip current. So if we look at the RCD, so you've got the different parts. So the list of components, you've got the incoming terminals on one side, the outgoing terminals on the other. You've got a reset button. You've got contacts, a solenoid relay, sense coil, your sensing circuit, a test button, a test wire. But important, the basic RCD does not protect against short circuit or overload faults. An RCD is supplementary to basic circuit protection unless it has built-in overload and short circuit protection, or an RCBO. It must be used in conjunction with an appropriate circuit breaker or fuse. Cool. So there's two types. You've got type A in New Zealand, according to 2007, 2.6.2.2 type of RCD. In New Zealand, an RCD shall, in addition to complying with clause 2.6.1, be of a type where tripping is ensured for residential alternating current and residual pulsating direct current. And then you've got type B. So we'll come into working that all EV chargers need to be protected by a type B RCD. So it's AC, ripple pulsating DC, and ripple free DC as well. So it needs to be able to protect against DC because it's an EV charger, because EV chargers spit out DC to the cars. Cool. And then we start talking about the RCBO, or residual current circuit breaker with overcurrent protection or overload protection. Cool. So there's a few types there. So you've got a slim line, double wide, and then that one is a 3-phase on the end there. And that's just a closer look at that middle one there. Cool. So an RCBO, a residual current circuit breaker with overload protection, is a combination of an RCCB and an MCB, providing protection against both leakage currents, earth faults, and overcurrent, overload, and short circuits. So RC residual current protection, so it detects leakage currents, earth faults, and trips if an imbalance is found between the live and neutral wires, preventing electric shocks in the same way an RCD or RCCB does. Overload protection trips when the current exceeds the rated limit for a prolonged time, preventing overheating and fire hazards in the same way an MCB does. And short circuit protection instantly trips when a high fault current flows due to short circuit in the exact same way an MCB would.
Stuart, there's no sound. coming
Okay.
through.
Yeah, don't worry too much about the videos. I don't know why they put them in. Cool. So yeah, the main difference between RCD and RCCBO is the fact that it includes the same mechanisms as a MCB, so the bimetal strip and the solenoid trip, as well as the toroidal coil tripping mechanism. Cool. So we'll talk about fuses. So first, high rupturing capacity fuses. So HRC fuses versus MCBs. So HRC fuses are designed for low voltage, high current installations where short circuit currents can be extreme. They interrupt fault currents in the tens of thousands of amps while maintaining accuracy at lower overload levels. A typical HRC fuse has a rupturing capacity of 80 Ka compared to 6 Ka for MCB. That's 80,000 amps. So the photos in the fuse, the photo there, so they're rated at 100 Ka, so 100,000 amps for its rupturing capacity, and it's a 200 amp, 415 volt fuse. Sorry, I just can hear my coworker through the glass here. Yep, cool. So construction. So HRC fuses come in various types, including capsule, offset tag, staggered tag, and center tag, but all function similarly. So those are the different types there. So you've got your two capsule fuses there. You've got your offset tag and your staggered tag, and then the center tag there. So they have a ceramic shell filled with quartz sand and a silver fuse element, which ensures precise current response. When connected to supply, current flows through the tag, cap, and fuse element. So operation, the fuse element generates heat proportional to the current flow, which is absorbed by the filler material for proper heat dissipation. Fuses are designed for specific conditions. General purpose fuses tolerate brief overloads but operate when heat isn't dissipated fast enough, while motor rated fuses allow longer overcurrent bursts to enable motor startup before tripping. So under overload conditions, the electric material will melt and open the circuit. Calls the HRC fuse operation. So under fault conditions, the fuse element overheats and vaporizes. A gap forms, creating an arc. The arc heats the quartz sand filler, triggering a reaction with silver vapor to form silver silicate, which is a very effective insulator. The silver silicate quenches the arc, stopping current flow. This process happens rapidly. HR fuses have a fast-acting cutoff characteristic with terminal resistance exceeding 100 mega ohms after operation. Cool. So you got your markings and labels. So standard HRC fuse has the manufacturer, so it's the company that supplies the fuse, a safety certification, so it ensures the fuse meets safety standards, a category of duty, so it specifies the fuse's voltage type, AC or DC, the maximum voltage, and the rupturing capacity. Has a standard written on it, so it defines the safety and compliance requirements. Fuse operation. It's got a part number, a unique code for identifying the fuse in stock systems. So you can call up, give them the part number, and they can find the fuse. And if they don't have it, they can offer you a suitable replacement. A utilization category. So it classifies fuses based on operating characteristics and fusing factor. And current rating, the continuous operating current without degradation. The other thing to know about HRC fuses, they don't like being exposed to outside weather. So if you have a meter box that has a cracked fuse holder and the meter box door doesn't shut properly, it's probably a good idea to replace the hinge on the latch on the door, as well as the fuse holder and the fuse as well, because you cannot guarantee that it's going to act correctly. Cool. So utilization category. So utilization category of fuses. So modern HRC fuses are labeled with two letters, a lowercase letter for fault type and an uppercase letter for time current characteristics. So the lowercase letter indicates fault protection type. So fuses starting with A protect only against short circuits and need additional overload protection, often used for devices with high startup currents like motors. And your uppercase letter defines the fusing factor and response time. So GG fuses, general purpose, operate at 1.5 times rated current within 4 hours. So close excess current protection. Whereas GM fuses, motor circuits, handle high inrush currents, but do not operate at 1.5 times the rated current in 4 hours. So it's coarse excess current protection. So whenever we talk about close or coarse excess current protection, we're always talking about 1.5 times the rated current and whether it's within or not within 4 hours. Cool. And then we have cartridge fuses. So this is the type of fuse you'd normally find inside of an appliance or inside a fluoro light fitting, which don't really come across too much anymore. So they're small enclosed cylinders made of glass or ceramic, housing a fuse link inside. They protect electrical appliances and circuits such as fluorescent light fittings. So sealed with metal caps acting as terminals, their ratings are stamped or engraved on one cap or the other. So you've got the primary markings on the fuse cap. So you've got T315A H 250 volts. So T means it's a slow blow. 315A means it's rated at 3.15 amps. I cannot remember what H stands for, and it's a voltage rating of 250 volts or less. Cool. And then you've got your fusible link. So the circuit protection operates thermally, not by current, found in heaters and heat producing appliances. It acts as a safety backup against overheating. It consists of two contacts held by a tension spring and a thermal pellet. When the pellet melts at a set temperature, the spring forces the contacts open, cutting off the supply. Also called micro temps, these small devices operate between 60 degrees and 250 degrees C. They are single use and must be replaced with the correct rating. Often bypassed for minor issues like dust block fans. This is unsafe as a fusible link prevents fire. Designed for overheating protection, they do not respond to current. So when they rupture, you need to replace it with the correct size one, not just bypass it. Otherwise, you might not. It will not. The circuit will not act correctly and may cause a fire. One example was a roller door motor that I serviced recently, or replaced actually, because someone had bypassed the thermocouple inside the motor windings because it was causing issues. And then the windings inside the motor melted, which was, going to happen. So yeah, we replaced the motors and I got 2 new motors for the workshop. Cool. So rewirable fuses, semi-enclosed fuses, obsolete. Throw them in the bin. Do not install them. Do not use them. If you get to a job and one is installed, please offer to upgrade the switchboard. It's better for the and just explain to the client it's just better for their own protection. So we will talk about it just because they do still exist. So construction and operation. A semi-enclosed rewirable fuse connects the supply to one terminal and the load to the other with a wire wrapped around 2 pins forming a circuit. This wire acts as a weak link and breaks under fault condition. So protection methods, overcurrent. So wire heats, melts slowly and opens the circuit. You can tell it's been an overcurrent issue because it's a clean fuse base with melted wire globules indicates this failure. Short circuit, a current surge vaporizes the wire, leaving black soot and copper deposits, showing the wire has effectively exploded. So if you want to watch this in action, one way to do it is to take a couple of lengths of 1.5 wire, hook them up to a 18-volt battery, and then try and jumpstart your car. We know this works because one of the tutors here did that. I will not name names, but apparently it was very, very well. Cool. So these fuses provide coarse excess current protection with a fusing factor over 1.5. Though this varies with the fuse's condition. They are now obsolete and non-compliant in new installations as they cannot handle modern short circuit current levels. With upgraded wiring systems, higher load currents increase the risk of greater fault currents. A new fuse can handle up to 1,000 amps, but its capacity declines after operation. Repeated short circuit exposure degrades the fuse, reducing its effectiveness and increasing fire risk. Yep, so only rated at 1,000 amps, but the majority of the time in new installations, when you're doing your fault loop impedance testing, you're routinely getting above 1,000 amps. So it was 1,000 amps new, maybe 800 after a few times exploding, and then 700. You can see how these fuses are no longer safe or obsolete. Does anyone here still have them in their house or where they're living? Do you guys still have rewirable fuses? Upgraded, good. I was gonna say it's a pity you can't put photos into the chat because I was gonna say quickly go take a photo and post it, but don't worry. Cool. And then you've got rewirable fuses, semi-enclosed, so that yeah, each time the fuse operates, its accuracy declines. Residue buildup can create leakage paths, altering the fuse rating. And safety issues, the semi-enclosed design. Removing the fuse carrier exposes live terminals accessible without tools. And in fault events, ionized gas is released, which is highly conductive. If circuits on multiple phases are close together, this can cause a flashover event. So if you look at the base of a ceramic fuse holder, there's one pictured there. You can literally touch both sides, both live and dead, of the fuse base. The modern plug-in circuit breaker type bases, the plastic ones, at least have plastic covers, and you need screws to get to the conductors. Cool, because the audio is not working, we'll skip this video. Cool, see ya. Overload relays. So a thermal overload relay is a protected device used in electrical circuits to prevent damage to electric motors. Yeah, I see what you mean, Cody. If they're the top and bottom entry rather than the back entry, yeah, those you can even get fuses like that, main HRC fuses in houses and main switches, which is always fun. Cool. So thermal overload relay is a protective device used in electrical circuits to prevent damage to electric motors and other equipment caused by excessive current or overheating. It is commonly used in motor control circuits as part of a motor starter. Thermal overload relay operates on the principle of thermal expansion. When excessive current flows through the circuit for an extended period, it generates heat, causing the relay's bimetallic strip to bend. This bending action activates a trip mechanism, which disconnects the motor from the power supply, protecting it from overheating damage. Yeah, so you can see there the different ways that the overload works. So one phase open circuit or overcurrent on all relays. Cool. So your key components. So you've got your bimetallic strip. So a strip made of two metals with different expansion rates. It bends when heated. The current sensing element. The relay is connected in series with the motor circuit to sense the current. Your trip mechanism, when the bimetallic strip bends beyond a certain limit, it activates a switch to disconnect the motor. Reset mechanism, once called, the relay can be manually or automatically reset. And then you've got an adjustment dial, which allows setting the relay according to the motor's full load rating. And we'll take a closer look at that Siemens overload relay there. So you've got your equipment designation label. So you can, that's one that you can take out and write on a small piece of paper and put in. You've got your manual automatic reset selector switch. So it can switch between manual and automatic. 3 is a stop button, which basically just opens the thermal overload. 4, complete order number on the front of the device. So it's telling you which terminals are what. 5 is your switching position indication and test function. Yep. 6, so you got a transparent cover. It's sealable, so it secures the adjuster knob for rated motor current, test function, and manual automatic reset settings. You've got an adjuster knob for rated motor current, a repeat coil terminal, so only don't worry about that. An auxiliary switch repeat terminal, and one normally open and normally closed auxiliary contacts, which you can sometimes use for an indication light, or it is for your coil for your contactor. So most overload relays plug into the bottom of the contactor. I haven't seen many that don't. We've got a few here in the workshop, but usually they're quite a bit more expensive than the ones that just plug into the bottom of the contactor. Cool. So you've got your types of thermal overload relays. So you've got your manual reset, which requires an operator to press a reset button after the relay is tripped. The automatic reset, which resets automatically after cooling down. And then obviously you've got your selectable ones, like the one we were just looking at. So the advantages of thermal overload relays. So they're reliable protection. They protect motors from overheating due to excessive current. They're also one way, because of that excessive current, if one phase drops out, it'll draw more current through the other two, so it will protect against that as well. You've got adjustable settings that can be set according to motor ratings. So depending on the size motor, you can change the amount of current that it will trip at. This is good because if you can buy a whole bunch of overloads and then you can adjust them per motor if you've got different motors that you've got set up in your work area. It needs no external power, so it operates using heat generated by the motor current, so you don't need to run a control circuit for it. It does it itself. Cost effective, it's cheaper than electronic overload protection systems. Cool, so disadvantages of them, they've got a slow response time and may take time for the bimetallic strip to heat and trip, making it unsuitable for very fast fault conditions, but that's why we have our HRC fuses and our MCBs. It cannot detect instantaneous overcurrent, does not protect against short circuits. It requires a separate fuse or circuit breaker, and it needs periodic calibration. So the setting may need adjustment over time due to wear and tear. So your applications of thermal overload relays, so your motor protection that's used in industrial and commercial motor control panels. Your pump protection, it prevents damage due to overload in water pumps. HVAC system, it's used in heating, ventilation, and air conditioning systems, and conveyor systems. It protects conveyor motors in manufacturing and logistics industries. For complete motor protection, a thermal overload relay is usually combined with contactors and circuit breakers in a motor starter circuit. So here you can see the contactor at the top with the thermal overload plugged into the bottom. For this particular contactor, the connection for the coil is mounted on the side, and below you can see the power circuit for a three-phase star connected motor. So you've got your three-phase circuit breaker, you've got your contactor for the coil C, and then you've got your overload for your contactor or OLC before your motor. So even though the power circuit is drawn with them separate like that, the physical connection is straight into the bottom of the contactor there. Cool. Surge protection devices. Who has, or an SPD, who has installed a surge protection device? And where did you install it? Yes, but where? Residential house? Oh, yeah, it was single phase or three phase? Didn't need the address. So surge protected devices. So surge protected device, or SPD, is an electrical device designed to protect electrical circuits and equipment from voltage spikes, transients caused by lightning, switching operations, or other electrical disturbances. Is commonly installed in electrical panels, power distribution systems, and sensitive electronic equipment. So if you look there, so we've got a diagram. So this is, so you've got an SPD, which is connected directly to the earth bar from the incoming circuit breaker, which in the event of a large current spike diverts that current down to earth rather than going through the sensitive loads. So the importance of a surge protection device, so electrical surges can damage sensitive electronic devices such as computers, TVs, industrial machines, and communication systems. So lightning strikes can induce very high voltage transients that can destroy wiring and insulation. Power grid switching or faults can cause voltage fluctuations leading to equipment malfunction. SPDs help in reducing downtime and maintenance costs by protecting electrical infrastructure. So SPDs work by diverting excess voltage away from protected equipment and safely discharging it to the ground. They act as a voltage sensitive switch that remains inactive under normal operating conditions, but activates when a surge occurs. Cool. So an SPD is the common name for a device made up of a voltage dependent resistor, or VDR. A VDR is a resistor that changes its resistance value depending on the voltage applied to it. The value of a VDR used for surge diversion is inversely proportional to the voltage applied. So typically the resistance value of the VDR will remain fairly constant for minor spikes. However, for the greater the voltage, the greater the change in resistance. For example, a lightning strike will cause the resistance value of the VDR to plummet, allowing maximum current to flow through it. Another part of the surge arrestor is a spark gap, which absorbs the energy as it flows through the device. Oh, just while we're going through things. All good, guys. That's the YouTube link for the channel that I post the videos to. So you can, if you can't see the thing, or if you have to go early or you arrive late, you can always go and check the videos there afterwards. That way everyone can catch up, and later on when we start to. Yep, so a surge protection device is more for residential or commercial and looks almost like a circuit breaker fuse cartridge is the hybrid that I would say, whereas the surge arrestor is more for your high voltage lines, which quite literally opens to break. So a surge arrestor, yeah. No, I don't think you would have to Google that. Cool. The key difference, so surge protectors are designed for individual appliances or small groups of electronics, while arrestors are used to protect entire electrical systems or large pieces of equipment. So it depends on the size of the equipment. So surge arrestor is a spark gap. So yeah, surge arrestor is more when you're talking infrastructure. I don't know why they've used surge arrestor there, but another should be another part of a surge protector is a spark gap, which absorbs the energy as it flows through the device. Yes, cool. So now we'll look at how fault protection works. So fault protection works on a number of factors. But here, so the inverse time, so current characteristics. So basically, the higher the fault current causes faster circuit protection operation. Fusing, tripping times vary by device type and fault current level, but they tend to follow the inverse graph. So basically, the operating time goes down as the current increases. So you increase one, you decrease the other. You decrease one, you increase the other. So basically more current, faster trip time, but obviously up to a point where it can no longer protect against it. Cool. So you got your cutoff characteristic. So the cutoff characteristic measures how quickly a protected device clears the fault. A faster cutoff reduces energy at the fault, minimizing stress on the cable. So you got the start of the short circuit there, the pre-arcing time. So before the arc, you've got the arcing time once it starts to disconnect. And then you've got the total clearance time is when the start of the short circuit and the finish of the arc. So when we're talking about the arc, we're talking about the arc between the two ends of the circuit protection device. So example, HRC fuse, the amount of time it takes for the short circuit to start, then that silver strip to break, and then the silver oxide to form and quench the arc, or how long it takes that arc to travel up into the arc chute of a circuit breaker. Yeah, so then we've also got the curve of the asymmetrical prospective short circuit current. So that it's cut off before the total, it can reach its total cutoff. Cool. So you've got fault clearing stages. So you got the pre-arcing time, the time for fault current to build up until the device trips. Arcing time, the time for the fault to fully clear as the contacts open, gradually reducing energy to zero. Cool. Then you've got your rupturing or breaking capacity. So it's the maximum current a protected device can safely interrupt as its rupturing capacity. It must exceed the prospective short circuit current or PSCC, which depends on circuit impedance. If underrated, the device may weld shut, keeping the fault in the circuit, or rupture violently, scattering debris. A properly rated device will safely interrupt the fault with minimal impact on surrounding equipment. So if you have a 6 kA breaker and it experiences a 10 kA prospective short circuit fault, if it welds itself shut, that current flow will continue, causing fire or electric shock, or it will explode, which could take out other parts of the board as well, causing fire inside the switchboard. One thing to ask your tradesman about if you're working residential or commercial is there is actually a part of the wiring rules that say we have to protect against the ingress or egress of fire in the switchboard by maintaining a closed opening. So basically, if you can fit your finger through the hole, you need to seal it. So when you install domestic boards, you don't break out every single punch out in the board. You only bring in the ones you need to, and then if the holes are too big, you need to seal it. I've got about 20 tubes of intermittent fire sealant at home. Even though it says it's expired, that stuff doesn't go off. I've asked fire engineers, that stuff doesn't go off. So if you're looking at protecting against lightning, short circuit current, you would need to talk to someone who's a bit more, because it's a huge amount of energy. Usually when we're talking about lightning strikes, we're talking about not direct strike, but indirect strike. So indirect strike is when it strikes near you and the static electricity released into the air is enough to generate fault current in the wires. And that's what your surge protectors are going to protect against. That's what your SPDs are going to protect against. But if you get a direct strike near your house or on your house, everything's going to fuse shut, and I'd be more worried about your house just being on fire. So with lightning strikes, we're more worried about protecting against indirect strikes rather than direct strikes. But that's a good question, and something I might bring up with my fellow tutors tomorrow, and we'll see if we can figure that out. Cool. So you got your category of duty. So protective devices, device marking, and duty category. So protective devices are marked with their voltage, current type, and rupturing capacity under test conditions. For example, an AC80 device operates with alternating current and has a rupturing capacity of 80 kA or 80,000 amps. Choosing the correct AC or DC device is crucial. AC arcs extinguish quickly as current crosses zero. DC creates continuous arcing, requiring stronger contacts to handle prolonged strain. So one of the big differences between AC and DC switches is that DC switches have a comparatively larger air gap between the contacts because of that arcing. Cool. So you got backup protection. So tuned circuit protection and backup devices. So some protective devices are finely tuned to their load, like a thermal overload relay for a 10 amp motor, allowing startup inrush but tripping on a sustained overload. However, these devices may not handle high short circuit currents, requiring backup protection like an HRC fuse to safely interrupt faults. So that's what we were talking about before with the thermal overload. Is that a thermal overload can handle, takes a while to interact. So if there's a large current spike due to a short circuit, we need those HRC fuses to help disconnect the supply. Cool. So HRC fuse protection. The fuse is rated to allow the overload relay to function and the motor to start. However, in a short circuit, the HRC fuse quickly interrupts high fault currents, preventing damage. The graph below illustrates the inverse time current characteristics of each protective device. So you've got your motor starter overload relay, and then you've got your HRC fuse link. So when we say HRC fuse link, normally for a motor, you will have an HRC fuse link where if one HRC blows, it disconnects the other two as well to ensure that all three phases are disconnected at once. And sometimes that facility will also disconnect the neutral. Cool. So discrimination. So no, we're not talking about discriminating against Indigenous people. We're talking about the discrimination of protective devices. So when we're talking about this, we're talking about installing them so that the one closest to a fault operates first, minimizing impact on the rest of the installation. So devices are wired in series, decreasing in size as circuits become more localized. So we look at the first example. We've got a 6 amp fuse, which is connected, and then there's a 5 amp fuse in a room. But because they're so closely linked together, close together in rating, the 5 amp fuse and 6 amp fuse blow at the same time. However, if we were to decrease the fuse in the room to 3 amps, the 3 amp fuse would blow and increase the one at the board to 10 amp. The 3 amp fuse would blow well before the 10 amp, so it would only take out the one room rather than all 4 at the same time. Cool, guys. So that's all we have today. I will stop sharing my screen. Cool. Cool. So any questions that people have, fire them out. Whether that be about the on jobs, off jobs, or stuff we've covered tonight. But yeah, update on block course. As far as I know, they'll be sent out soon. I have been kind of poking that bear, and now that the LSM mark is back, that'll hopefully move things along. Also on that note, make sure you guys are doing off jobs. Yep, all good. Yeah, we can jump on a call after this is finished. I'll actually stop the recording now because so your on jobs, so block course be in March sometime. Yep, as far as I know, it's in March. On jobs mark. So once you've submitted it, it goes to the assessment team, and then they work through it and get it assessed. For your on jobs, no, there is no deadline on your on jobs. Okay, I would submit a learning support request about the on jobs you can't see. And as far as the deadline for on jobs, no, there's no deadline for on jobs. There's only a deadline for off jobs, which is the just the standard 4204 stuff on the Learning Hive. No, there's no deadline for on jobs because you can do those once you've even finished your year 3 exam. That's what happened to me. I had to do my own jobs after I'd finished my exam. I'm just going to open up my email address now so I can open up the calendar. And then I can tell you exactly when they're supposed to be. So looking at the calendar. So there's a year 1 block course starting on the 26th of May. And one starting on the 9th of June. So they're not in March, they're in May. Yeah. Oh yeah, so 3207 testing. So if you guys do okay. Yeah, I've actually, let's jump on the Learning Hive. I can probably have a look. Yeah, so those are the Lower North or the ones for the Wellington Training Centre. They may be different for otherwhere else in the region. Yeah, so before you get access to 32607, you gain access to your remaining on-job assessments once you've completed unit standard 32607, which is applied knowledge of working safely in the electrical industry. Cool, but other than that, guys, you guys are more than welcome to log off. I will again post the video on the YouTube.